Hello, I'm Rachita Agrawal, and today I will be presenting my FYP project on the topic of towards interpretable and robust occluded facial recognition. Here's the table of contents. I will cover the background, previous research and identify the gap, research objective, methodology and experiment results, conclusion and future work. Let's start with the background. The demand for facial recognition is increasing rapidly in the field of deep learning for applications such as security, surveillance, and personal identification. According to Market and Markets, the facial recognition market is growing at a compound annual rate of 16.6%, indicating the need for more advanced technologies. Keeping this in mind, my final year project will focus on a new approach that enhances the accuracy and robustness of the system, especially in real-world scenarios where faces may be occluded or distorted due to various factors. Moving on to previous research and gap. Technology solutions exist for improving the accuracy of facial recognition. However, challenges still exist in the real-world scenario, especially due to face occlusion, light and pose variance, etc. One existing method, which is one of the reference researchers for this project, utilizes deep CNNs as well as feature masks to handle occlusions. As you can see here, on the image on the right is a feature mask, and the orange box correctly depicts the location where the mask exists on the image on the left. However, you may notice that this image here is a synthetically occluded image which has the mask superimposed on the person's face. Therefore, such a model, when tested for real occluded face images, fails to provide a good feature mask. As you can see here, for this image, which is a real occluded image where a person is wearing a face mask, the model completely mispredicts the location of the occlusion. Moving on to the objective. The objective is to develop a more robust framework for handling occluded facial recognition in real-world scenarios. With this objective set, we move to the methodology and experiment results. These are the three key methodologies that we experimented with, which I will be talking about further. First, let's talk about building feature dictionaries. A feature dictionary captures facial features such as the eyes, nose, and mouth, which are lost in degraded images to build a feature dictionary. As you can see here, we start with a training data set of around 450,000 facial images. We pass it through a model called the LResNet50IR. This model stands for the lightweight ResNet50 model of the inside face recognition variant. This model is specifically used for facial recognition tasks since it is trained to extract features from the face images that can be used in various applications such as face recognition and face verification. This model is cut at an intermediate layer so that we get feature maps. From these feature maps, we can select features and choose to cluster them using K-means algorithm. Once we do this, we get the cluster centers. These cluster centers are the most represent the most representative facial features, which then comprise of the feature dictionary. Next, we will see how we will test the feature dictionary. Here, in this pipeline, we have a test image, which is an occluded face image. Again, it's passed to the same model, cut at the intermediate layer. We get the feature map representing the image. Now, with this feature map, we take our feature dictionary and calculate the maximum cosine similarity distance between each descriptor in the feature map versus the dictionary centroids. Hence, we get a heat map, which represents the similarity scores between these two. Now let's look at the results. So here, as we can see, we have two images. First one is occluded with a face scarf. The other one is occluded with goggles. So we experimented with different versions of the CNN model, cut at the last layer, second last layer, and third last layer. As we can see, the model which is cut at the third last layer gives promising results where the shape of the face and the location of the facial features are still preserved. However, we still need to make sure that the model focuses more on the occlusions so we can filter this occlusion noise out. Next, therefore, we talk about enhancing the facial dictionary using transformers to further eliminate the occlusion noise. Transformers are an advanced form of CNNs which learn entirely based on the self-retention mechanism. It first extracts features by encoding the output, then it decodes them and learns the contextual relationships between the input sequence. As we can see here, the first half of the pipeline is pretty similar to the feature dictionary. However, once we reach the transformer, which is the encoder-decoder architecture, the dictionary is fed to the decoder of the transformer for enhancement. Due to the self-retention mechanism of transformers, the transformer is able to leverage on the features extracted from the CNN as well as the dictionary to improve the output and provide us with an improved feature dictionary. The crossface loss is used for backpropagation. The crossface loss is a loss used for facial recognition, and we get output feature maps. Now, this technique is therefore able to provide us with the most representative facial features which will be fed to the facial algorithm and improve the accuracy. This is done by the improved feature dictionary. Finally, this technique is superior to feature masks, which was described in the existing method due to the self-retention mechanism of transformers. This helps it to assign different weights to different dictionary features based on their relevance to the current prediction tasks. However, due to constraints on the available computational resources, both speed and memory, we could not complete the run for the transformers code. Therefore, this approach is incorporated as a future work for this project. Moving on to the second topic, which is feature pyramid networks. This technique was proposed to improve the performance of CNNs for object detection using feature pyramids. The core idea was to enable the CNN to detect objects at multiple scales of the feature map by creating feature pyramid networks. The first step in this process in the process of this experiment would be to create purposeful occluded images from the Cassia web face dataset. So we choose around 100k dataset images and purposely occlude them. These refer to occlusions that are placed on the face as they would be used practically. Next, we get model predictions from different kinds of models and get feature maps as outputs. Again, from these features, we can cluster these features separately using VMF clustering, which is a spherical clustering method, and then visualize these clusters using PCA. PCA is required since these features are actually high dimensional as they come out of CNN model. Therefore, to visualize them in a 2D plane, we need principal component analysis. Hence, we will be able to observe the separation between the clusters and hence determine whether the model is able to separate out the noise, which is the occlusion noise, occlusion features versus the facial features. As you can see here, feature maps of different sizes are extracted from the FPN and experimented with. We can see that we experiment with a backbone CNN of ResNet 50 plus FPN with a feature map size of 56, 56, 256, and so on. As you can see here, in the last row, we see that we have only experimented with the LResNet 50 IR model. Now, it seems like the ResNet plus FPN model seems to separate out the clusters in a much better way than just the LResNet 50 backbone CNN, as evident from the diagrams. However, since we reduce the number of dimensions via PCA to just 2, a bias may be introduced since 2 dimensions might not be the most optimal reduction. Due to such a bias introduced by PCA, we may not be able to correctly ascertain if the models can separate the noise and clean features out well by just looking at the visualizations shown on the previous slide. Therefore, we choose to cluster the noise and clean features separately and obtain the cluster centers, as shown here. Then we test for another unseen 100 images, which are occluded purposefully as described earlier, pass them through the model, get feature maps, and then calculate the minimum cosine distance between the previous cluster centers and the current features. From this, we can get the percentage of correct assignments, which ascertain if the features are correctly assigned to the occlusion or the facial cluster. The results of this look as follows. Here are the percentage scores. As we can see that the scores for the CNN plus FPN model are better than the LResNet scores. However, the difference is not very high for us to conclude that this current FPN model will be able to outperform the existing occluded facial recognition methods. Therefore, we need to come up with better ways to improve such a model. With this, we move forward to the third technique, which is the UNet plus LResNet 50 IR encoder model. In this project segment, we explore image segmentation as a method to detect occlusions from facial images. The key advantage of image segmentation is that the exact area of occlusion can be differentiated from the visible facial features of a person, unlike the feature masking, which draws a rectangle around the occlusion. Therefore, the aim is to detect the exact boundary of the facial features so they are not masked out and increase the accuracy of facial recognition. The image segmentation model UNet, as shown here, is one of the simple image segmentation models that separate the different regions of an image into image segments. It consists of an encoder-decoder structure where the encoder downsamples the images using a CNN backbone, getting the most informative features at the bottom, and the decoder upsamples to return to the input image resolution as the output. At the beginning of the project, we fine-tuned a pre-trained UNet model on a benchmark segmentation dataset known as the Cityscape datasets. Since most of the state-of-the-art models have been tested on this, we can compare the performance of our model easily with this. The score that we will use to evaluate is the mean intersection over union score. These are the IOU results. As we can see that our results are around in a range of 55 to 62%. The MIU scores on Cityscape's dataset for state-of-the-art models, however, are in the range of 80 to 89%. These models have a higher MIOU score due to their complex networks mainly. Due to time and resource constraints, we could only experiment with 10 epochs per model for batch size of 1 and a lower image size. Therefore, the observed MIOU scores are lower. And we believe that if a model is trained for more epochs, we can at least reach a range of around 70 to 75%. So therefore, we can conclude that UNet can be used for further experimentations. Now, the LResNet model is integrated with the UNet model by being fused into the encoder of the segmentation model. This model architecture of the hybrid model, as shown here, is for the LResNet model, which is cut at layer 3. So as you can see, we have one convolutional layer, then we have one ResNet block and another ResNet block. We also experiment with other cuts at layer 3 and layer 4 and layer 5 of the LResNet model. These diagrams are too big to be depicted on a slide, therefore they are skipped. Here, while the training for the model is done on a large-scale face image dataset, which is used for segmentation tasks, the testing is done on real occluded images. Again, the MIOU scores are calculated for the hybrid model and compared against benchmark scores. The results here show that the scores are slightly low for being at par with state-of-the-art models which have a high score of 80 to 90%. However, this model still managed to beat the performance of the existing facial recognition method that we've been discussing so far. Looking at the results here, so these images are from the real occluded dataset that we talked about earlier. On the left-hand side, we can see that these are the segmentation results. The segmentation results actually give us the visible part of the face and filter them out. These features are, as we can see, that the exact boundary of the faces have been captured by the segmentation result, which is a good sign. However, we can see that when these same real occluded images are passed through the from paper, the occlusion pattern that is detected by it are completely off. We can see that none of the images actually are able to, none of the feature masks are actually able to capture the right location of the occlusion. Therefore, we can conclude that the existing method does not perform well on real occluded datasets. However, our model is not perfect. Like we saw earlier, our scores are a little low than the state-of-the-art models. Therefore, we see that there are some errors where, for example, the eyes are not properly captured by our segmentation model. Similarly, here, the mouth of the person is not completely captured. So there is definitely some scope of improvement for this model. Moving forward, we will look at how this model performs on synthetic occlusion dataset. Firstly, we can note that our model is actually able to capture the exact outline of the person's face which is visible. However, we can see that for the paper actually mispredicts on this particular image. It is not able to capture the exact shape of the mask and predict the feature mask correctly. However, our model still excels in this scenario as well. Another case here is that where a model is actually not able to correctly capture certain parts of the person's face. Therefore, again, there is still room for improvement. Moving on to the conclusion and future work section. In this research, we explored 3 different deep learning approaches to improve the robustness of occluded facial recognition systems. The image segmentation model, UNet, gave us the best results out of the 3 approaches. In contrast, the feature dictionary, transformers, and FPN models require advanced techniques to beat state-of-the-art models. We noted that the feature dictionary we built has the potential to improve further as it contains noisy features despite our efforts to only include the relevant facial features. Therefore, the transformer enhancements is required as part of the future work. For the hybrid FPN plus ResNet backbone, even though it beat the performance of compared to just CNNs, the separation of the different feature clusters need to be further improved for the hybrid FPN model to beat state-of-the-art facial recognition models. For this, advanced feature fusion techniques can be explored for FPNs to improve how they can retain information from all the CNN layers. Finally, as we explored UNet and image segmentation model with the LResNet50IR backbone as the encoder, we conclude that such a model has the potential to filter out the occlusion noise from a real occluded facial image. This hybrid UNet model beat the performance of the approach in the current existing research by producing a segmentation map that detected the face even when the approach failed in the research, as we saw earlier. Therefore, this model can improve the accuracy of facial detection algorithms in an unconstrained domain, building a more robust algorithm and satisfying the primary objective of this project. For future work, other deeper segmentation models can be experimented with, and the LResNet50IR can be integrated again, like shown earlier, to achieve more accurate results. These final inferences show that we can explore models such as UNet++, which is a mixture of both UNet and FPNs. Finally, these approaches can be integrated with the entire facial recognition pipeline to build an end-to-end robust model. In conclusion, facial recognition remains an open ground for modern researchers as the world moves to the era of digitization and artificial intelligence. The various techniques researched in this project to satisfy occluded facial recognition are just one of the constraints from which facial recognition systems need to be robust. As the real world becomes more and more complex and unpredictable each day, advanced security systems are gaining more demand. To keep up with this growth, more robust and accurate facial recognition systems must be developed to satisfy this need for high performance. With this, I come to the end of my FYP presentation. Thank you.